Now let's get to grips with the strong nuclear force and let's have a typical nucleus over here. This is a typical nucleus. In fact, this one is a neutron, this one is proton, neutron, neutron, proton, proton, neutron, neutron, proton, proton. So this is a typical nucleus. Let's consider two protons. This one is a proton and this one is a proton. There must be the force of repulsion between these protons because these protons are light charges and these protons are going to repel each other. Yes or no? This proton is getting repelled in this direction and this proton is getting repelled in this direction. There is a repulsive force and there are protons in the nucleus, so these protons are getting repelled. Yes. So my question is that why does this Coulombic force fail to break the nucleus? Yes, I am repeating my question. Why does this Coulombic force, or you can say why does this electrostatic force fail to break the nucleus? What's that reason? What should be the reason? And if you will be talking about the neutrons, neutrons are the silent spectators. These neutrons will do nothing, but these protons will get repelled. My question is why? Why this nucleus is stable? Why does this Coulombic force fail to break the nucleus? Can it be a gravitational force? Is there a gravitational force acting between these protons? Because in fact these protons carry mass, so there will be a gravitational force. But when calculated, the value of gravitational force is very negligible in comparison to the Coulombic force. So gravitational force doesn't do anything here. Then why? Which one keeps the nucleus bound? Which one keeps the proton bound? Or in fact, in other words, you can say, which force keeps this nucleus bound? My question is that. So there is another kind of force which are operating here. And that is called nuclear force. That is, this one is another kind of force which is operating here, and this one is called nuclear force. And this is operating between protons, this is operating between neutrons, or this one is operating between both. If I will be telling you this is a proton and this one is a proton, so there will be a nuclear force. This is largely attractive in nature. So this nuclear force is going to attract these protons, will keep these protons bound together. In other words, you can say this nuclear force will keep this nucleus bound. Clear pause. So this one is a proton and this one is a proton. It gets attracted. There is a nuclear force. Let's say this one is neutron and this one is neutron. There is a nuclear force, there is a large nuclear force between these two neutrons too. And if there is a proton, there is a neutron, still there is a nuclear force. So nuclear force doesn't depend upon the charges. Is that clear? It doesn't depend upon the charges. Even if it acts between the protons, it acts between the neutrons, it acts between the proton and neutron. Clear? Now let's talk about the range of this nuclear force. It's short ranged. The range of this nuclear force is very short. You can say it's short ranged. It's short ranged force. That is around 10 to the power minus 15 meter. For the separation, that is about 10 to the power minus 15 meter. It's very large. It gets strengthened. It's very large and even much larger than the Coulombic force. And that's why these protons, or you can say the neutrons, or say the protons and neutrons are bounded together. Is that clear? Now, if we will be talking about the separation, that is larger than 10 to the power minus 14 meter, if we'll be talking about the separation which are larger than 10 to the power minus 14 meter, this nuclear force is is not stronger. In fact, the value, the magnitude of this nuclear force is very less when we are dealing with the separation which is more than 10 to the power minus 14 meter. But for the separation that is about 10 to the power minus 15 meter, it's very large, even much larger than the Coulombic force. So just recall Rutherford size of nucleus, that is about 10 to the power minus 15 meter, and the whole story is inside nucleus. The whole story goes on within the nucleus. Is that clear? I hope this one is clear. Now let's come to the weak nuclear force. What's that weak nuclear force? Yet another kind of force which are operating when the interactive particles are neutrons, protons and electrons. So there is another kind of force which are operating when the reactions involving neutrons, protons and electrons take place. Yes. So before giving a dissertation on this weak force, let me deal with the two notions. The first one is beta negative decay and the second one is beta positive decay. Fine. What's that beta negative decay and what's that beta positive decay? So let's discuss about beta negative decays. So there are neutrons within a nucleus. In a nucleus there are neutrons. So neutron changes itself into a proton and simultaneously emit electron and a particle called antineutrino. Once again I am repeating my verse here, that in beta negative decay neutron changes itself into a proton and simultaneously emit an electron and a particle called antineutrino. Let's check it out with an example. Let's say this is a nucleus. This one is a nucleus. It contains protons and neutrons. Say this is number of protons here, and this one is neutron, and this is A. This is mass number. Fine. I told you that in beta negative decay, neutron changes itself into a proton. Fine. We have another nucleus here. So here I told you that neutron changes itself into a proton. It carries n-1 and it carries chat plus 1. And this remains same. This mass number remains same. And simultaneously an electron is emitted and a particle called antineutrino is emitted. The concept of antineutrino, this will be a separate video will be available. That will be dealing with the concept of antineutrino. So this one is the beta negative decay. So here this one is electron. This is electron because the charge gets conserved. That's why we have written here an electron, or one electron is emitted because charge needs to get conserved here. Now if we write separately this one, so there is a neutron here, and this neutron changes itself into a proton plus electron, an electron is emitted and a particle called antineutrino is emitted. Fine. But one more caution I would like to give you here. You should be cautious. Please do not think that neutron is made up of a proton, electron and antineutrino. This is a misconception. Please do not think that neutron is made up of proton, antineutrino and electron. So this is about the beta negative decay. Now let's deal with beta positive decay. In beta positive decay, what happens? proton changes itself into a neutron and simultaneously emit positron and a particle called neutrino. I am repeating my words here. Here what happens? Proton changes itself into a neutron and simultaneously it emits positron and a particle called neutrino. Let's write here. Let's say this is a nucleus and this nucleus has jet protons and neutrons, and this is the mass number. So I told you that this proton changes itself into a neutron. So there is another nucleus. So this proton changes itself into a neutron. Just match this equation. This is different. Here what is happening here, that one proton changes, that's why Z minus 1, and it gives one neutron. It changes into one neutron. That's why n plus 1. Is that clear? Now this remains constant and simultaneously emits positron and a particle called neutrino. If I will be separately writing this one, this one is a proton here, and this proton changes itself into a neutron and simultaneously emits positron and a particle called neutrino. Is that clear? This is positron, this is E plus, because charge needs to get conserved. So this is about the beta positive decay. So what is happening here? What is happening? If I will be telling to draw out the very peculiarities, what will you draw? Here you see that one particle changes into the other. Here one particle changes into other. So the change of the transformation of the particle takes place here, in fact. So these changes, how these changes are taking place? There is a force which is responsible for these changes, and this force is called the weak force. Clear? This force is called the weak force. There is a force which is responsible for these changes, and this force is called weak force. If you will be discussing about the range of this weak force, the range is even smaller than the size of a proton, or a neutron. Clear? Now it's the weakest force which is operating in nature. It's the weakest force. And before that I discussed about the nuclear force, and this one is the strongest force. This strong nuclear force was the strongest force which is operating in nature. And now let's come to the weak nuclear force. This is the weakest force. I can say this is the second weakest force. This is the second weakest force. This is the second weakest force operating in nature, and the weakest force was gravitational force of attraction. Is that clear? So, which is the strongest force which is operating in nature? Strong nuclear force is the strongest force operating in nature. Which is the weakest force operating in nature? This gravitational force is the weakest force operating in nature, and this is the second strongest force operating in nature. Is that clear? And this is the second weakest force operating in nature. So let's have a comparison. Let's do comparative study. Let's do the comparative study. Let's do the comparison here. Let's say this is a strong nuclear force. This is the strongest force operating in nature. This is the strong nuclear force. This is greater than electromagnetic force. This is greater than electromagnetic force. and this is greater than weak force, and this is greater than gravitational force. This is the comparison. If we will take the value here as 1, it's going to be 10 to the power minus 2. It's 10 to the power minus 13, and this is 10 to the power minus 38. What does it infer? This electromagnetic force is 100 times smaller than the strong nuclear force. Electromagnetic force is 100 times smaller than the strong nuclear force, or you can say this strong nuclear force is 100 times greater than the electromagnetic force. This gravitational force is 10 to the power 38 times smaller than the strong nuclear force, or in other words, you can say this strong nuclear force is 10 to the power 38 times greater than the gravitational force. This weak force is 10 to the power 13 times smaller than the strong nuclear force, and this strong nuclear force is 10 to the power 13 times greater than the weak force. This is all about the comparisons. So friends, hope the things have been clarified. Do subscribe and share for more conceptual videos. Thank you very much.